understand the main idea behind zero noise extrapolation, and also a little bit, we won't go too deep into the theory of dynamical decoupling, but we'll talk about it, and we'll talk about how to use these two techniques. And then, like I said, we'll demonstrate how to use these in some sort of quantum data flow pipeline. All right, so first we need to ask, what is quantum error mitigation? Like, what is the thing that Mitiq is implementing and trying to do? And so quantum error mitigation is really the acceptance of, our quantum devices are noisy. Not all of us are hardware engineers. Not all of us can go and fix that problem directly or try to. And but we still want to be able to use them, right? We still want to be able to get results out of our quantum computer that are still somewhat useful, right? We don't want everything to be affected by noise. While they're noisy, can we still make use of them? And there's a lot of things that happen on quantum computers that affect the desired outcome. There's incoherent noise, there's coherent noise, there's spam errors, which are state preparation and measurement errors. Crosstalk is a big issue on modern devices. Calibration errors, so when you think you're doing one gate, but maybe you're doing like that gate, that rotation plus a little bit of theta. And plenty of other things. For example, cosmic rays have been something that I've been hearing about recently, as they cause highly correlated errors, and it's really hard to fix those. And the general idea with quantum error mitigation is, when you run a job on quantum hardware, you send a circuit off, you do that unitary, you do some measurements, right? And you get some ideal distribution for what those measurement counts kind of histogram out to. And this is kind of what we're representing here. Now, when you actually go and run your job on some actual hardware or a noisy simulator, you don't get that ideal distribution, right? You get something maybe that's a little bit more spread out. You get something that is not centered on your ideal value, and it makes your computation almost not useful. The idea with error mitigation is let's try to align that distribution in line with what the ideal value is, but there's always a price to pay, right? If we increase the accuracy, we have to give up some amount of variance, at least for many of the methods that we're going to talk about today. And so the goal here is to, like I said, bring things in line with the ideal distribution and figure out, how we can do that. So there's lots of different methods available in the literature for how to do this. Zero noise extrapolation is one of the most popular, if not the most popular, and it's relatively simple, both conceptually and to use. It's relatively straightforward. Probabilistic error cancellation has been a really hot thing over the past few years, but it's a little bit more difficult to apply because you need some knowledge about what's happening on your quantum computer. You need to understand what type of errors are happening, and then you need to go about fixing those errors in some sense. And then dynamical decoupling is another, again, relatively straightforward, conceptually simple technique, and again, relatively straightforward to apply. There's lots of other techniques out there, learning-based techniques. We have a learning-based version of probabilistic error cancellation in Mitiq, as well as currently we don't have any symmetry-based techniques in Mitiq, but it's definitely something that we're thinking about and potentially putting on our roadmap. All right, so one of the questions that we often get is like, how does error mitigation compare to the thing that I've maybe heard about called error correction? And error correction was, really put on the table by Peter Shor just a year after, he found one of the first, real algorithms to make people care about quantum computing. And, so he came up with this way to basically fix errors that happen on a quantum computer. And so that was 1995, we're almost 30 years later, and why are we talking about something that's not just this? And so error correction, if you're unfamiliar, is a way to fix errors by encoding logical qubits into many different physical qubits. In a sense, you're spreading entanglement around. And then you do intermediate measurements, you produce syndromes, and then you look at those syndromes, and it'll tell you roughly, hopefully, what error happened on your quantum computer. And then, based on what error happened, you can maybe apply an X gate here or a Z gate there and fix those errors. Error mitigation on the other side is a little bit different, right? We're not trying to fix errors as they happen. We're saying, let's perform multiple, potentially different noisy computations. Let's collect the results and then see if we can combine those different results to infer, interpolate, extrapolate to an ideal expectation value. And error correction is scalable, but currently it's unfeasible. We don't have enough qubits to, do large scale experiments. We are just started, we're like pretty much on the edge of, being able to do smaller scale quantum error correction experiments, and we have started seeing those in the literature. But we're talking, a very limited number of error corrected qubits. Error mitigation on the other side is in a lot of cases unscalable. So as we get devices that are more and more qubits, it becomes harder and harder to use error mitigation, but it's currently feasible. It works, very well on a lot of current devices. And I put the asterisk here next to unscalable because there's a lot of literature and research going into how to make error mitigation more scalable. And one of the techniques we'll talk about, dynamical decoupling, basically is infinitely scalable in a sense, right? We're going to be adding some gates to the qubits, but not in such an extreme way that we're incurring tons of overhead. So that's just some background in where to frame and where to put error mitigation in your head, in contrast, but also in conjunction with error correction. All right, so the first technique I want to dive into a little bit is zero noise extrapolation. And the key idea here is, we can't scale noise down, unfortunately. If we could, we would just do that. But instead, we'll actually increase the noise, and we'll figure out, using some extrapolation techniques, maybe we can go back to the zero noise value. So, this is an equation that would, kind of govern the dynamics of your system, right? We have the von Neumann equation, and then we have this noise term. And lambda is kind of a non-physical constant that we add in there that controls how much noise we actually have. And so the idea here is, we can make this plot where on the x-axis we have this non-physical parameter that we've introduced, and on the y-axis we have the observable, the expectation value for the observable that we're interested in measuring after performing our circuit. And from 0 to 1, this region is completely inaccessible to us, right? The noise happens, and we can't stop it from happening. We just take that approach. So we can't get data points in that region, but what we can do is get data points, 1 on that line, and 2 outside that line, right? We can, in some sense, drive up the noise. Yes, this is the Lindblad equation, by the way. And yeah, so we can get some data points outside this region, and we can do the very smart thing of drawing a line to extrapolate those points and see, okay, where does that intersect the y-axis, right? And in that sense, that's why this is called zero noise extrapolation, right? We get some data points and we extrapolate backwards towards where the zero noise limit would be. So the next question is, how do we actually scale the noise up? So in the first paper that this technique was introduced in, it introduced the idea of pulse stretching. So right, when you're actually trying to control qubits, you're sending pulses to them. And a lot of times what you can do is if you have access to that level of control, you can just send the pulse over a longer duration of time. You can say, okay, you do have to reduce the amplitude so that you're not doing too much of something, but you can just do it slower. And in a lot of cases, that just gives the qubit more time to have a mistake, have an error. And that's great. Unfortunately, as quantum programmers, we often don't have access to pulse level access to a machine. It has become a little bit more common, but part of the goal with Mitiq is to work on any device you want to work with, and each device kind of has a different way of accepting pulse level control. And so we've come up with a few different techniques for scaling noise that are device agnostic. And so we call these unitary folding techniques. So if this is the circuit of interest here down the bottom middle, and you want to increase the noise of it, the first method is to do this thing called local folding. So instead of just doing the gate and then going straight to the 2-qubit gate, you can do the gate, but then you do the inverse of it, and then you do the gate again. And then you do that again for the second gate and the third gate. And as the astute among you will realize, like, the first 2 gates in the sequence are going to compile to the identity, right? You're just doing the gate and then you're doing the inverse of it. And so in effect, the circuit is doing the exact same thing as the original circuit, but now it's much longer. So that's one way. Another technique is just take the entire circuit, do its inverse, do it again. Same exact thing, same effect, scale noise up. And then the last one is you can actually just insert identity gates in between these gates, so that the qubit is waiting around for more time in between actually doing the physical operations that you care about. So these are all ways to scale the noise up, and all of them are implemented in Mitiq and give you choices as to what to use, and we can talk about why you would use each one differently. But like I said, a lot of these are implemented so that people can go off and do research and figure out what is working best for them. So what does it look like to actually run a quantum program in practice? So, and I want to introduce this so we can figure out where Mitiq sits in this process and how this works. So the user writes a quantum program, and they're going to send it off to some sort of hardware or simulator to be executed or to be run. And then that hardware or simulator gives them back some results. And error mitigation and Mitiq sit kind of in between these 2 blocks that we've shown here. So the user is still going to write some quantum program, but then when they send it off, what error mitigation does is it generates some intermediary circuits. It executes all of those different circuits on the hardware or simulator, and then it returns the hardware or simulator will return multiple noisy results, whereupon the error mitigation then takes them and, like in the case of zero noise extrapolation, interpolates or extrapolates them to return a single value, right? So even though we ran lots of different circuits, we're getting one result in the end. And so just to go back here, you can imagine the data point at lambda equals 1 would be the circuit of interest. You're just sending it off like you would normally. The data point out here, the second one, could be maybe you fold the entire circuit 1 time. So now it's 3 times as long. And then maybe the next data point is you fold it 2 times. So now it's going to be extra long. And because as the circuit scales, you're more likely to have whatever types of errors are afflicting your machine, you get a result that is degraded in its accuracy. So that's the general idea. We have, I have some code that I can demo now. Are there any questions before we kind of jump into some of the code portion of this? Anything general about Mitiq or yeah, error mitigation in general before we look at some code? Okay, so just quickly, you should be able to see my terminal now. So just in case, let's see, where did this go? Okay, just to create a new environment, what I did was I created a new Python environment with conda create -n QRISE. That's the name of it. That's what I called. And then I'm going to use Python 3.11. I've already run this, but if you're following along or want to follow along, feel free to set up a new environment or just install Mitiq. Once that's created, we can activate QRISE. And then I use Conda to install pip because we're in the virtual environment. Doesn't necessarily come with anything installed. And then we can just pip install Mitiq, and that should just work. If you've done that, you can validate that Mitiq is installed by running pip list, and then you can search for Mitiq just by running something like this. And you can see right now I'm on 0.34.0, which I'm pretty sure is the latest version of Mitiq. All right, so that's getting things set up. Now let me share some code. All right, so the first thing that needs to happen when using Mitiq is the definition of an executor. And so the executor is the thing that Mitiq is going to use to go and run your circuits. So Mitiq works with hardware, works with simulators, works with, if you write some custom API that accepts circuits and runs them on the cloud, you can use all of that logic as long as it's abstracted away in an executor. So all Mitiq is going to do is it's going to run the function that you give to us, but it doesn't actually care what actually happens in that function. You could return 0. You could just return 0 every time. That's fine with Mitiq. It doesn't care if anything quantum is actually happening, but we want something quantum to happen. So we need to take this executor and add some noise to it. So one thing we can do is we can define this a new object, noisy circuit, and we want to add noise to the circuit. So we're just going to do a simulation here, and we should just be able to do circuit. I think this is the API. Let me just yep, and then to add depolarizing noise, depolarizing, and then we need to pass in some sort of noise strength. So which is just called P. And we already have this noise level variable in here. So we'll just pass that in. Noise level, if I could spell. And then you can see it's complaining to us here about this not being used. So we'll add in noisy here. And yeah, we're just going to do a density matrix simulation, and it's going to return the probability that the state is in the all 0 state. So no matter how many qubits we have, we're just checking to see, are we in the ground state? All right, so I've made sure that the Python kernel here is running in the environment that I set up, and that seems to be running. And you can see here, so we imported Circ. Mitiq is mostly written in Circ, and so Circ is a mandatory dependency. So I didn't have to install Circ in order to get this running. If you want to use Mitiq with Qiskit, Pennylane, any of the other front ends that you like using, then you will have to install that. But otherwise, we can just chug this along. Okay, so now we have our executor. Now we need a circuit, right? So we need a circuit of interest, and we're going to first walk through applying zero noise extrapolation with Mitiq. We'll then demonstrate what dynamical decoupling looks like, and then lastly, we'll end with something related to the Unitary Fun Challenge, which is stacking these two techniques on top of each other so that you can, potentially get more accurate results. All right, so to define a circuit, we first need to define some qubits, which we can do with the circ functionality, and then we define we're going to do Hadamard 2 C0s, and then I'm adding an S gate in here just because we need something to demonstrate what happens when you do unitary folding, because as you probably know, the Hadamard and the C0 are their own inverse. So it's hard to see what's happening if we don't have something that has a dagger. All right, so what does this look like? Pretty straightforward. If anyone has trouble seeing the size of stuff, just let me know, and I'm happy to zoom in. but otherwise I'll take it to be okay. So this is our circuit of interest. And now, as part of the zero noise extrapolation process, we need to generate some circuits that are longer. And so we need to do this unitary folding action. So here we have two options available to us. There are others, but these are just two I'll demo first. So let's just do fold gates at random, which is really just the fold local method that I showed. And so we need to pass in the circuit, and then we need to pass in a scale factor. And the scale factor is basically how much longer than your original circuit do you want this folded circuit to be. So just to start, if I pass in 1, I'm going to get the same thing, right? I want the new circuit to be 1 times the length of the previous circuit. If I pass in 3, then I should have this nice thing, which is every gate gets folded right after itself. So here we've got 3 Hadamards instead of 1, 3 C0s instead of 1, and then this layer of 3 C0s with 3 S gates. And this is exactly why I put the S gate in here, because S is not the inverse of itself. Now, you can also do other scale factors that are not odd integers, right? You could do scale factor equals 2. And this is why it's called fold gates at random, because if you try to double the length of this circuit, you can't do the naive thing of every gate its inverse itself, right? Because otherwise you're just going to scale it 3 times. And then when you do it again, you do that 5 times. And so if we run this again, you can see, oops, it's not the same every time. So there is some randomness in here. And then, so that's like the fold local. We can also do fold global. And again, I think we need to do the odd scale factors here. Well, so you can actually see, so when I do scale factor equals 2, it will try, but it's not always super accurate in how closely it can hit exactly that scale factor equal to 2. So it will do some approximating. But 3, you can see we do the original circuit, we do the circuit in reverse with the inverses, and then we do the circuit again. And then again, you would probably do something like scale factor equal 5, scale the noise up even more. And you could go even more if you wanted to, just keep on adding. Okay, so that's the ways in which you would scale the noise up to generate these points, lambda equals whatever. And then we need to learn how to do the extrapolation part. So there's lots of different ways that we can do this. You can let's see. You can choose lots of different scale factors. For example, you can choose like this one, 1, 3, 5, but there's nothing stopping you from using way more scale factors than that. The one limitation is the more scale factors you choose, the more circuits you're going to have to run, right? And if you are, worried about the cost of how much this thing is going to cost to run on a real device, or if you're worried about you have some decoherence time limits, then you can't just run the scale factor as to 100 and expect like, oh, I'm still going to get anything that's not just like completely a state that's completely depolarized. So just something to be aware of when you choose scale factors. But yeah, so and then the other option is what actual extrapolation technique do I want to use? Do I want to use a linear fit? Do I want to use an exponential fit, some sort of polynomial? All things that you can decide and affect, what I want to say. Depending on your noise model, you may want to choose one of these over the other one. If you know that your signal that you're looking for is going to exponentially die off as you As you add more noise, then you probably want an exponential fit. If, however, you're in the regime where doing a scale factor 135 is probably not going to kill your signal exponentially, maybe it's slowly dying out, then maybe you want a linear fit. So all things you can take into account how your device is working to tune what's happening in the error mitigation. So with this, we can define, in this case, we're going to do an exponential fit called an exp factory. We define this factory, and then we can basically ask it to run some experiments. So you can see here, the input circuit is very short. This may reduce the accuracy of noise scaling. So first, that's one thing it's telling us, and something to be expected. This is not a deep circuit. I don't want to sit here waiting for a simulator to run to show you something interesting. Generally, yeah, you probably won't see that if you're running anything interesting. And then the other thing it tells us is like, okay, the extrapolation fit may be ill-conditioned. Likely more data points are necessary. So it tries to tell you, when it thinks it's not going to do super well, which is good. But and you can see here, this is actually, I'm not exactly sure why it's warning about the extrapolation warning. I think it's just a default out of SciPy. But you can see, we are getting a degraded signal, the degraded expectation value of measuring something in the zero state. And the other thing to notice here is, so this is our original circuit. The ideal value for measuring the probability of the 0, 0 state is 1/2, right? The S gate is just a phase thing. It's not actually doing anything. So this is just a GHZ circuit, right? And so we're going to have 1 over square root 2, 0, 0, 0 plus 1 over square root 2, 1, 1, 1. And you can see when we just run our circuit, it's doing a pretty good job. It's getting 0.048 something. Then when we scale things up, it's, we're seeing a degraded signal, but when we extrapolate back, we're getting extremely close to 0.5, which is the ideal value here. So, and that's one other thing to notice, which would be kind of interesting. Let's say we make this noise level a bit stronger. So instead of 0.005, we'll do 0.05, which is, it is kind of a lot of noise. But just so we can see what this looks like, you can see now instead of more of a linear exponential fit, we do see a little bit more of that curve, and it still is, getting something that's a bit more accurate. And you can see, these data points are much worse than what we previously saw, right? The other one was 0.49, and now it's below 0.4, but it's still able to extrapolate to something that's pretty good. Let's demonstrate some of the other techniques that are available here. So Richardson extrapolation is a polynomial of degree 1 less the number of points that you have. So we should see basically a quadratic fit here. And again, you can see we're shooting for 0.5. It's a little bit under, but it's still way better than if you just ran this a bunch of times, and you're going to get something that's centered around 0.39 or something like that. And then lastly, we can check the linear factory just to see how that performs. And again, this is probably not the right extrapolation technique. It's easy for us to say that given we know exactly what the ideal value is. Obviously, when you're running something interesting, you don't know what the ideal value is. But that's just to demonstrate. And one thing to note here is this technique is built straight into Mitiq, so you can do some pretty nice exploratory analysis when you are trying to run stuff, and hopefully we make that easy for you just to explore. So let's try something a little bit more. It's not so much interesting as it is like, let's push it a little bit more. The GHZ circuit is cool, but it's super small. one of the things we can do in Mitiq, we have some benchmarking circuits. And a randomized benchmarking circuit, which is what RB stands for, is a circuit whose total effect is the identity. So let's just take a look at one of these. So you can see there's lots of stuff happening in here, lots of random stuff. But if you were to have a really good compiler, a really good tool that is able to take unitaries and squash them down into a single unitary, then you would find that this operation is actually just the identity. As for how it's generated, don't ask me that. It's all we know is that the ideal expectation value for the 0, 0 state, if you feed in 0, 0, is 1. Okay, so there's our circuit. And what we just did in walking through zero noise extrapolation here was the long way around. It doesn't have to be that individual of a step in terms of scaling the noise with the circuits and then picking the noise scale factor, or picking the noise scale factor in the extrapolation methods. You can simply use out of the box Mitiq's ZNE.execute with ZNE. And so there's default parameters in here. For example, I'm pretty sure it's defaults to Richardson extrapolation with scale factors 1, 3, and 5. But you're welcome to pass that in. I think it's just factory equals ... and then scale noise, you can pass in whatever you want. So, but just to demonstrate the use of the default parameters, what we're going to do is we're going to execute our circuit with a noise level of 0. So we're going to figure out what the ideal value is, which, like we know, should be 1. And then we're going to see what the noisy value is. And then we'll compare with what Mitiq gets by using zero noise extrapolation. So we can just run this cell. And okay, we're seeing that there's no improvement. So I must have messed something up here. Let's see. So this circuit is randomized, but there's nothing added at the end.
Does it matter that the noisy underscore value equals execute circuit without a noise level being set?
I believe there is a default here, so I think that should be fine. Let me make sure I ran this right. I mean, we were seeing the right behavior in here, which is good. The thing that I'm surprised by, wait, what is a little bit of live debugging here? True value. Okay, so, okay, now for whatever reason, it's working. Thank you, Brian. Whatever you said scared Mitiq into working again. So yeah, maybe the noise level was just too high. It is quite a deep circuit, so I think that's probably what it is. We had the noise level too high to actually see any benefit, and that's that's one thing to be aware of. If your noise is too strong, there's just nothing you can do about it, unfortunately. So now we can see the error with Mitiq without Mitiq was 0.5. The error with it is 0.2. So we're definitely seeing some improvement. We can print out here also the what actually was the ZNE value. And okay, so it's not great, but it's quite a bit better than what the noisy value would have been. Noisy value. How is this not defined? I see. I can't spell. Right, so there's quite a bit better, but it's not perfect. So I had in here just a short exercise. I think just for the sake of time, we should skip it. But the idea here was there's some code in here which we can define what is our inference method, what is our noise scaling method, and you can kind of just play around with all of the different options in here and see what's the best, how accurate can you get. So there's a question from David. How much more benefit would you see if you made scale factor even larger, 7, 9, something bigger? That's a great question. It's very problem dependent. It's very what's happening on your device dependent or simulator. I mean, I'm happy to demonstrate. Let's look at what happens if we go 1, 3, 5, 7, 9. So as we saw, yeah, so linear fit is, I think just by looking at these data points, you can see linear fit is probably not the best thing to fit here. So maybe we try, let's just see what happens with the Richardson first, and then we'll try the exponential. So with the Richardson, you can see it's kind of doing what I would call an overfit. And just in terms of fitting each one of these data points exactly. And that's exactly what Richardson extrapolation does. But yeah, it's I'd say it's fitting them a little bit too closely. So maybe we try an exponential fit and see how this does. But I generally would expect, oh, this is also, oh, okay, sorry. I was thinking that we were running the GHZ circuit still, but this is actually now running the, what's it called? The randomized benchmarking circuit. So as we can see, the exponential one is fitting the best. It's almost exactly telling us the answer is 1. And I think you kind of can see from the data points that this could be some sort of exponential. But the other thing that you see is as you increase the noise scale factors, a lot of times you do just approach some noisy value, which in this case seems to be like a quarter. For the probability of measuring the 0, 0, 0 state, or the 0, 0 state, because we're working on a 2-qubit, which kind of makes sense because there's 4 states. There's a 0, 0, 0, 1, 0, 1, 0, and 1, 1. So it's basically just complete noise. You're just picking one at random as you increase the noise to infinity, basically. So I guess my recommendation here is basically like, you can try to figure out exactly where things approach this limit and then go close to that, but no need to like, I would say these 2 extra data points are kind of redundant. And you can maybe get away with like, okay, what if we got rid of 5 and then just did these, right? So maybe we get rid of 9 too. So there's nothing that say they have to be equally spaced. And you could even say, let's do a non-integer, a non-odd integer, and get slightly different results. Sweet. Okay, so this is something to play with. I'm happy to forward along this notebook after this, and if people want to go plug and play, happy to see what you're able to get. But I do want to go over quickly just dynamical decoupling as well in the last few minutes that we have. And for dynamical decoupling, we need a circuit that has some idle qubits. And by idle qubits, I just mean qubits that don't have any operations on them for some period of time. And the GHZ circuit is a good one for this because, a lot of them just have 1 or 2 operations. Otherwise, they're idling. And again, this comes from the Mitiq benchmarks module. And so what dynamical decoupling does is, there's a saying that's like something that goes something along the lines of like, the devil makes work for idle hands. And that's basically what's happening here with the qubits, right? The devil makes work for idle qubits. Stationary qubits are really hard to control. They often just decohere, but it's sometimes a little bit easier to control qubits when you're telling them to do something, right? We're almost better at telling telling qubits to do an X gate than we are at just saying like, just sit here for a little bit, please. So basically what's happening here is, let's just look at this first qubit. So we had the Hadamard and then the control not, which happened before, and then it just sat there. Now instead of just sitting there, we're going to do what's like an XX pulse or an XX sequence, right? So obviously that's just the identity, but we're occupying it with something to do while it's trying to sit there idling. And basically, it's going to use this rule that we've added, rule.xx, and say anywhere where I can fit a double X gate, I'm just going to do it. And like I said, try to keep the qubits idling, try to keep them from idling, and do that. Now, there's other sequences we can do in here. For example, XY is another sequence, but it doesn't necessarily fill up the space as much as the XX rule does, right? It's a little bit too long to fit in these other sequences, fit in these other spots. So, and then you can define all sorts of custom rules if you want to do, I don't know, ZZ or, you know, whatever you come up with, Hadamard. And then basically, so I guess I don't have it here, but let's see. If we do DDD dot execute with DDD, and we pass in our circuit, or we should really pass in the GHZ one because that has the idle windows. And then we're going to pass the rules. Oh yeah, I need to actually tell it how to execute. And again, we're getting something that's somewhat close to 0.5, which is the ideal value here, but not perfect. And that's kind of the idea here with error mitigation. It really takes some precise, you have to know your machine, you have to know what's going on and really play with this stuff kind of a lot to get it to give you, you know, really good results. So that's dynamical decoupling. As you can see, there's definitely a lot less overhead with this technique as there is with zero noise extrapolation, right? Where here we're not only running larger circuits, but we're also running different circuits, right? We're running these different noise scaled circuits. Here, we're just occupying idle qubits and then averaging some results like you would if you're normally just running with some measurements. Okay, lastly, just in the last few minutes, the Unitary Fund Challenge for QRISE is about stacking different techniques and understanding, you know, how much of better performance can you get from using, say, probabilistic error cancellation and dynamical decoupling over just using a single one of those techniques. And Mitiq is built with the capability of doing this in mind. So not only can you just run dynamical decoupling with a function like this, execute with DDD, but you can also apply a decorator to your function that'll take care of it. So every time you run new execute, it runs with both ZNE and dynamical decoupling. So here we just need to tell it what rule to use. So let's say, I don't know, ddd.rules. Let's try XY. And let's see, for the factory, maybe we do Richardson factory with scale factors 1, 3, 7, since we saw that kind of worked before. And then just as a new way to scale noise, we can do insert ID layers. So we saw in the presentation that one of the ways to scale noise is just to insert identities between qubits, between operations. So now we define new execute to just be our previous execute function, but with these two techniques stacked on top of each other. And I need to import this function, which comes from here. So let's just do that. And boom. So now, when I run this new execute, and it should be, let's see, I actually don't remember, what is circuit? So it's the randomized benchmarking circuit. And, you know, it's pretty long. It's not really getting the result that we would potentially expect, but there's only a few, actually, I don't think there's any places in here it can insert a DD XY sequence. So that would maybe be a bad choice. Even in here, it can't insert it because there's only 3 gates here. So maybe we don't want to try something else. And then maybe the Richardson extrapolation is really bad. Maybe we want to do a linear fit. Anyway, these are all things to play around with. I just wanted to demonstrate the fact that it's relatively straightforward to stack techniques using the decorators. But with that, I'm going to stop sharing. Like I said, I'm happy to share slides, notebook after the fact. Just let me yeah, put stuff online, and then I can pop it in the Slack channel. But yeah, any questions relating to anything I talked about today? Perfect. I'll assume that it made perfect sense. And yes, I could definitely share the notebook. Amy here, yeah, happy to.
Yeah, I should have like a small question about the zero noise extrapolation. So are we basically just increasing the depth of the circuit and hoping like the noise is kind of gonna correct itself out over a longer period of time?
So it's not necessarily that the noise is going to correct itself. Like I see what you mean in terms of like some sense of averaging when you increase the depth. But what we're actually looking for is when you increase the circuit depth, you actually want a more noisy result, right? You want to see your signal kind of like degrade, or I mean, it could go up too, but like that's just dependent on what you're actually looking at. Um, and yeah, I mean, the theory of the technique, I should mention for zero noise extrapolation, there's no theoretical guarantee that this works. There are theoretical guarantees for other techniques like probabilistic error cancellation. It has a little bit more, I guess, theoretical backing to it. But zero noise extrapolation in the literature has worked for a lot of people and continues to be one of the main front running techniques, partly because of its simplicity and its easy. But it doesn't, yeah, unfortunately, right now does not have the theoretical backing to it. And then I see dynamic decoupling is the addition of identity operators through the circuit to avoid idling. Why is it called that? Um, so it is identities, but right, it's like complicated identities. And why is it called that? So the technique has been around for a long time, way before, or in the early days of creating qubits in a lab. And part of the idea behind this technique is to decouple uh, entangled systems. And so in some sense, when you apply gates, if you apply XX pulses, XX gates to a qubit, there is potentially some way in which you can like get it to disconnect from the environment, another qubit, a qubit that you don't want it to be entangled with. Um, and you can do it on the fly. So I'm pretty sure that's why it's like dynamic, as in you can do it while the circuit is happening, and decoupling because you're trying to say like stop interacting with the environment and start interacting with what I'm telling you to do. Yeah, thanks for the question, David. All right, well, if there's any other questions, I'm happy to take them. If you tag me in the Slack, which I am there, on QRISE, I will try to get back to you as soon as I can. I will post my stuff in there, and yeah, I should add if you're interested in any of this stuff, the Unitary Fund has a Discord where we organize. Please feel free to jump by. I'll post a link here in the chat to join. discord.unitary.fund. And yeah, always we have weekly meetings on Fridays about Mitiq. So if you're interested in learning more about it, how to use it, how to do research with it, it's probably a good place to get started and come chat with some of myself and the other developers that are working on this project.
If you also have any questions, I'd recommend you get them in now. Otherwise, thank you so much, Nate, for coming to present that QRISE. This was a really helpful workshop. Yeah, for anybody who's like interested in stuff, I definitely also recommend just like the read the docs that are on the GitHub. I was just like following along from there as well, and I found that really helpful. Actually, that's a question I need. Okay.
Yeah, so briefly describe dynamical. So let me just show the screen again. I think that could be just to be quick. So dynamical decoupling is a technique where that takes the understanding that idling qubits decohere very easily, and so it's almost better to do something with idling qubits than it is to just like try to get them not to do anything. So this is a circuit that you might want to run a GHZ circuit, and there's lots of idling qubits, right? You're asking them to sit still for a long period of time. And so dynamical decoupling is a way to insert operations that in effect are not going to do anything, right? They compile to the identity, but they occupy the qubits for some period of time. And in essence, that's all the technique is, right? You just insert some of these sequences. It shouldn't affect any of the measurement outcomes, but hopefully your qubits are less error prone because of it. That's the idea. And yeah, like Mahir said, our documentation, I hope, is pretty good. If you're interested in learning more about this kind of stuff, we do have a user guide on dynamical decoupling, which I just posted a link to in the chat. So definitely check that out.
I think that's all. Yeah, just for everybody, Nate will probably be posting the slides and then the Jupyter Notebook will put in the announcements as well, and we'll have the video of this recording, the video of this meeting put up on our YouTube channel. So anybody needs to go back and see. Yeah, I think that's all. I'll close this meeting in a minute. Thank you again, Nate, for coming to present.
Yeah, thank you.